In this presentation, I'll focus on how replication can help us strengthen psychophysiology as a science by improving its robustness, transparency, and credibility. Imagine this situation. You come across a fascinating psychophysiological finding in a publication, something striking, something you believe could be a solid foundation for your own research. You design a new study to build on it, but you get no effect. This is actually a common frustration among researchers. We invest time, energy, and funding into work that sometimes leads nowhere because the original effect may not have been robust to begin with. Additionally, it is a waste of resources. So, if a study cannot be replicated, can we really say that the phenomenon exists? Earlier studies have shown that more than 60% of null results are never even written up, and another 15% are written but never published. This means that the literature presents a biased picture where mostly positive findings are published. This is known as publication bias, the preference within the scientific publishing system for results that are statistically significant or that confirm the researcher's hypotheses. Researchers often ask themselves, should I or even can I publish my null findings? And many end up not investing their time and effort to write or submit them at all. This is what's known as the file drawer problem. This file drawer problem is linked to a broader issue, a kind of external censorship that shapes what gets published and what doesn't. Reviewers, editors, and even funders may discourage or reject papers when the effects are non-significant or not considered interesting enough. There's also a strong preference for novelty, new, surprising, even controversial findings over confirmatory studies. Topics that are sexier, more attention-grabbing tend to be favored, while replication or incremental work often struggles to find a place. Projects promising breakthroughs are much more likely to receive support than those that try to replicate existing evidence. The result is that replication has become what some call the orphan of science. Everyone agrees it's essential, but few actually want to adopt it. Replications are also seen as low prestige and can even create conflict with the authors of the original studies. So, despite being vital for scientific progress, replication still struggles to find its place in the system. These problems have also contributed to the use of what we call questionable research practices. One example is p-hacking, sometimes described as data fishing, the misuse of data analysis to find something, anything, that comes out statistically significant. With enough analytical flexibility, you can almost find a p-value below 0.05. As Ronald Coe said, if you torture the data long enough, it will confess to anything. Luck and Gaspelin illustrated this by showing how it can be easy to obtain significant ERP effects and why we should not do so. There's also pure harking or charking, when hypotheses are changed after seeing the data, turning exploratory findings into what appear to be confirmatory. As Chambers argues in The 7 Deadly Sins of Psychology, these practices may seem minor, but they erode scientific credibility. This analytical flexibility is also very common in psychophysiology research, since raw data passes through complex pipelines, from artifact removal to statistical modeling. At each step, researchers make decisions which will shape the final outcome. Studies have shown how big this problem can be. For example, one study found that after having 70 teams analyzing the very same dataset, their results varied dramatically depending on their choices. And even subtle changes in pre-processing routines can lead to different conclusions. So, the danger is that preferential analytical choices may result in fishing expeditions. It's important to remember that replication studies also face many challenges, and they're not immune to publication bias. Some authors have discussed what's been called null hacking or the gotcha bias, situations where researchers might be motivated to disprove prior influential studies. However, the evidence for this phenomenon remains inconclusive. Moreover, it is important to recognize that replication outcomes are not binary. It's not simply a question of replicated versus failed to replicate. Another problem is poor reporting. A review of 150 ERP articles in several journals showed that many authors still don't provide enough detail about their methods, processing pipelines, or data. Moreover, editors and reviewers are not consistently enforcing these guidelines. So, we end up with a situation where a large proportion of studies simply don't give the information to reproduce their work. A further issue is small sample sizes and, as a result, low statistical power. Since psychophysiology research is characterized by very time-consuming data collection and analysis, many studies may end up having a small number of participants. For example, Clayson and colleagues 2019 estimated an average sample size of 21 participants per group in ERP studies. But what is the problem with low power in practice? It inflates effect sizes, reduces the likelihood that significant results actually reflect true effects, and ultimately undermines replicability. In addition, we tend to celebrate the lone genius, working independently. But strong and reliable science is rarely the work of one individual. Scientific progress depends on collaboration, on sharing knowledge, data, and resources. So, one important solution is team science, larger, multi-lab collaborations that allow us to collect bigger, more diverse samples and to build evidence that is not only statistically stronger, but also more generalizable. So, what can we also do to address these challenges? First, we can estimate a priori the sample size to achieve adequate statistical power. Second, pre-registration may reduce analytical flexibility by specifying the aims, hypotheses, method, and planned analyses before we run the study. Third, we should be open about exploratory analyses. We may develop hypotheses after seeing the data, but we should declare them as exploratory, not confirmatory. Fourth, openness is key. Sharing data, code, and materials enables other researchers to check, reuse, and build on our work. Fifth, preprints help to facilitate open access, making findings available more quickly and widely. The editorial and the scientific community also play a vital role, such as creating special issues that explicitly invite non-significant findings. Another solution is the use of repositories such as OSF, Zenodo, GitHub, or NeuroVault by sharing the research process, materials, data, scripts. Journals and organizations are also using incentives, like badges, which recognize and reward these open practices. Furthermore, the development of policies in journals for registered reports and for replications to value these practices. Here we can see the difference between conventional publishing and registered reports. In the traditional model, researchers first plan and conduct their study, then submit a manuscript to a journal. The peer review happens only after the results are known, and acceptance often depends on whether those results are positive, novel, or significant. In contrast, with a registered report, the study plan is submitted to the journal before data collection. This goes through what's called Stage 1 peer review. Reviewers evaluate the importance of the research question and the quality of the methods. If the plan is accepted, the journal commits in principle to publishing the study, regardless of whether the results turn out to be positive, negative, or null. After the study is conducted, the manuscript goes through Stage 2 peer review, which checks adherence to the approved plan and the soundness of the interpretation. But crucially, publication no longer depends on the outcome. So registered reports turn the focus back to rigorous methodology and transparent research questions, reducing publication bias and questionable practices. Another important step is the increased interest in replications. For a long time, replication studies were considered uninteresting and very difficult to publish. Schmidt in 2009 called replication the neglected concept in the social sciences. But things started to change with the rise of open access journals like PLOS One, although the real turning point came with large-scale replication projects, such as the Reproducibility Project in Psychology, published in 2015, involving 270 researchers over 5 years. It showed both the scale of the problem and the resources required to assess replicability. As shown in the graph, the number of replication and reproduction studies has risen in recent years. But it's worth noting that overall rates remain low, estimated at just about 1% of published studies. So, while progress is real, replication is still far from being a standard practice in science. Nevertheless, these efforts have had an important impact. As we can see on the left, several journals have started making recommendations and supporting replication studies. And new methodological advances have been proposed to make replication more feasible. So, why do replications matter? Replication builds trust in science. It helps confirm which effects are reliable and to identify false positives or spurious findings. Replication also enables correction and prevents wasted resources by discouraging further work on unreliable findings, which is critical for building cumulative knowledge for both theory and applied interventions. Replications also provide training value for early career researchers by teaching good scientific practice. In short, replications are not about double-checking, but essential for credibility, correction, and cumulative progress of science. Before moving on, let's clarify a conceptual distinction in replication. On one end, we have direct replications. These use the same theory, the same hypothesis, and as closely as possible, the same methods as the original study. The goal is to test whether the original effect can be reproduced under the same conditions. On the other end, we have conceptual replications. These still test the same underlying theory or hypothesis, but they do so with different methods. The idea is to check whether the effect generalizes beyond the original design. Because resources are limited, we have to be strategic about what to replicate. Priority is often given to studies with high theoretical or practical value, or those that are highly influential, for example, measured by the number of citations. Also important is when the original evidence is weak, such as having a small sample, questionable research practices, or incomplete reporting. Eisiger and Collegias in 2023 proposed a decision model based on the replication value, which is essentially the value of a study multiplied by the level of prior uncertainty about it. It is always a good practice to seek feedback from the original authors before data collection, and even to use approaches like adversarial collaboration or red teaming. Another useful step is to check whether replications already exist. We now have searchable databases, such as the FORRT replication database. Other initiatives include the Institute for Replication and Replication Wiki. These tools allow researchers to track replication attempts, to see what has been replicated, with what outcome, and under which conditions. And how do we decide whether a study was replicated? There are several criteria, and my advice is to see the FRED package with 7 functions for R, because I cannot go into detail here. But to have an idea, some are based on significance. For example, checking whether the replication shows the same significant result as the original, or whether a meta-analytic combination of both is significant. Others are consistency-based, asking whether the replication effect falls within the confidence or prediction intervals of the original, or whether the results are statistically homogeneous. There is also the small telescopes approach, which uses a metaphor introduced by Jacob Cohen. If your telescope is too small, you cannot expect to see distant stars. In the same way, a study with low statistical power cannot detect very small effects. This approach tests whether the replication effect is not so small that the original study would have almost never observed it. Thus, replication findings are not a simple yes or no, and using distinct criteria affects how we interpret the evidence. Let me give you some concrete examples of replication studies. In 2012, German and colleagues published a study on social exclusion and body temperature, and they measured the temperature in the index finger. It received large attention, both in the media and in academia. However, it had a small sample size and was conducted in single lab in the Netherlands, and therefore considerable uncertainty. Recently, Lazarevic and colleagues started carrying out a multi-lab registered replication and extension of this study. This replication effort involves a consortium of several laboratories across countries and regions, spanning 3 different climatic zones. Each lab is recruiting around 50 participants for a total sample size of at least 500. To ensure comparability, all labs are using the same equipment, including smartphones, temperature sensors, and weather monitoring devices. This equipment is being circulated among the participating labs to maintain identical measurement conditions. Additionally, this project is an extension of the original. Participant skin temperature is measured at different body sites. Room temperature and humidity are monitored with 2 devices, and additional self-report measures are included. Each sensor is connected to a smartphone, and the phones are color-coded to track which signal is being collected. All data are transmitted online to the coordinating lab server. To evaluate the replication findings, we will combine significance and consistency-based approaches by defining 3 levels of evidence. Weak, the effect is significant and in the same direction as the original. Medium, the effect is significant and its confidence interval overlaps with the original. Strong, there is no significant difference between the effect sizes. We have not pre-registered a meta-analysis, but variability across labs will be modeled. Another example of a large-scale replication effort is the EEG Many Labs project, published by Yuri Pavlov and colleagues in 2021. The organizational structure included a core coordination team, an advisory board of EEG experts, and independent replication teams. In total, 24 highly influential EEG studies were selected, all characterized by relatively small samples, but high scientific impact. At least 3 independent laboratories are replicating each of these studies. On the right, you can see 2 examples highlighted in red, corresponding to the 2 Amadeo replication studies in which our team is collaborating. This figure also shows the citations and the main psychological domain of each original study. We can also see on the EEG Many Labs website that, at this phase, these 2 studies have completed data collection and are in the process of writing the final paper for submission. These 2 studies by Amadeo and colleagues have been highly influential, but are based on relatively small samples and have not been replicated until now. This registered replication submitted to Cortex involves a consortium of 8 laboratories from several countries, each recruiting around 40 participants. It also integrates both studies into a single design combining EEG measures and questionnaires, making it also an extension. Because this is a collective study, we could not share the same EEG equipment as we did in the thermoregulation study. As a result, we worked with different EEG systems. Some labs used brain vision, others biosemi, and so on. Despite these differences, the goal is to ensure that the results do not depend on the system used. In addition, 6 analysis pipelines were developed in eGlab, and all labs use the same script on their own raw EEG data. 3 scripts follow the original Amadeo studies by relying mainly on manual pre-processing of the data, while the other 3 apply recent pre-processing standards. This approach allows us to examine whether the success of the replication depends on analytic choices. Regarding the evidence for replication, we proposed consistency-based criteria. First, we will examine cross-lab consistency by estimating the effects separately for each site. Second, we will conduct an internal meta-analysis, combining results across all labs to estimate the pooled effect size and assess whether this effect is significant in the same direction as the original, and if its confidence intervals overlap with those previously reported. So, the key message is that replication is a pillar of scientific credibility, an opportunity to build stronger science. It also requires a collective effort from researchers, journals, funders, and educators. As Popper put it, only by repeated testing can observations become truly scientific. And as Ventura argued more recently, without replications we risk publishing with bias, or even perishing as a credible science. And with that, I'd like to thank you all for your attention. A special thanks goes to my students, to Cátia Silva, and to the collaborative networks that make projects like these possible. Replication is, above all, a team effort, and I'm grateful to be part of such a supportive scientific community.